Quasi-hereditary algebras, lecture 4, quasi-hereditary algebras. Let us start by recalling the definition of a highest weight category. Let A be a finite dimensional associative and unital algebra over an algebraically closed field K. Let L1, L2, and so on Lm be a complete and irredundant list of representatives of the isomorphism classes of simple A modules, written with respect to some chosen linear order on these classes. Let P1, P2, and so on Pm be the corresponding indecomposable projectives. This means that Pi is an indecomposable projective cover of Li. Let delta 1, delta 2, and so on delta m be the corresponding standard modules. So they are defined in the following way. So delta I is the quotient of Pi modulo the trace in Pi of all the projectives Pi plus 1, Pi plus 2, and so on up to Pm. Now recall that the category of all A modules with respect to our chosen linear order on the set of isomorphism classes of simple A modules is called the highest weight category, provided that the following two conditions are satisfied. Condition 1, for any I, the kernel of the projection from delta I to Li has a filtration whose subquotients are Lj, where j is strictly smaller than I. And condition 2, for any I, the kernel of the projection from Pi to delta I has a filtration whose subquotients are delta j, where j is now strictly bigger than I. Now let us discuss the notion of a heredity ideal. Denote by J the Jacobson radical of A, that is the maximal nilpotent ideal in A. Alternatively, J is the intersection of the annihilators of all simple A modules. Definition: an ideal I in A is called a heredity ideal, provided that this ideal is idempotent, that is, I times I is equal to I. The next condition is that if we now plug in J in the middle of the product of I with I, so if you consider the product of I times the Jacobson radical J times I again, the outcome should be 0. And finally, the ideal I should be projective as a left A module. For example, the 0 ideal is obviously a heredity ideal. 0 times 0 is 0, 0 times j times 0 is 0, and 0 is a projective left A module. Here is another example. Let A be the path algebra of the following quiver. We have two vertices, 1 and 2, and an arrow A from 1 to 2. Consider the ideal I, which is generated by the trivial path at 2. Then this ideal is a linear span of this trivial path, epsilon 2, and our arrow A from 1 to 2. Then the claim is that this I is a heredity ideal. Indeed, I square is equal to I because I is generated by an idempotent. So it is generated by the element epsilon 2, and this element is an idempotent. Next, I times the Jacobson radical consists just of the element A, times I is equal to 0. This one can check by direct computation. The point is that A times A is 0, and A after epsilon 2 is also 0. So this product is 0. And the ideal I is projective as a left A module because it is just the direct sum of two copies of P2. If you consider this linear span, the only thing which acts in a non-zero way on the left on these elements is epsilon 2. So it is just a direct sum of two copies of P2. So all conditions are satisfied, and this means that our ideal I in this example is a heredity ideal. Now let us look at a more involved example. Let us assume that A mod is a highest weight category with respect to some partial order less than or equal to on the set of isomorphism classes of simple A modules. Define the ideal I as the trace of the projective module Pm, so M is a maximal index, so the projective module Pm coincides with the standard module delta M. So we consider the trace of this projective module in the whole algebra A, and we define our ideal I as this trace. So the claim is that this is a heredity ideal. Of course, if we take a trace of any module inside the left regular A module A, we will get an ideal. So this is indeed an ideal. Now let Em be a primitive idempotent which corresponds to Pm. That is, Pm is equal to Aem, and Em is an idempotent, and Em is a primitive idempotent. Then the ideal I is by definition equal to A times Em times A. So the trace of the projective Aem in A. This is just multiplication. So in particular, I is generated by an idempotent, so I squared is equal to I. Since each Pi has a standard filtration, the trace of delta M in Pi is a direct sum of copies of delta M. In particular, this trace is a projective module. But since the left regular module is just a direct sum of copies of various Pi's, this means that the whole ideal I is projective as a left A module. Finally, we know that Lm does not appear as a subquotient of the radical of Pm. That's the first condition in the definition of a highest weight category, so the surjection from delta M to Lm should be filtered by smaller symbols. So from this it follows that if we take the trace of Pm inside the Jacobson radical times Pm, we will get 0. As a formula, this means that A times Em times J times A times Em is equal to 0. But of course, J is equal to Aj, and we can also multiply on A on the right, and then we get exactly that I times J times I is equal to 0. And this proves that our ideal I is indeed a heredity ideal. Now we can define the notion of quasi-hereditary algebra. Definition: an algebra A is called quasi-hereditary provided that there is a chain of ideals. So we start from the 0 ideal, which we denote by I0. So this is embedded into I1, this is embedded into I2, and then all the way up to Ik, which is equal to A. So this is a chain of two-sided ideals in A, and the condition is that the subquotient II modulo II minus 1 should be a heredity ideal in the algebra A modulo II minus 1, or any I. A comment on terminology: such chain of ideals is usually called a heredity chain. For example, consider the path algebra A of the quiver with two vertices 1 and 2 and an arrow A from 1 to 2. Then we have the following chain. We have the 0 ideal, which embeds into the ideal generated by epsilon 2 and A. So that's the ideal which we considered as an example a couple of minutes ago, and this embeds into A. So we have already seen that this ideal in the middle is a heredity ideal, and of course the quotient of this algebra by the ideal generated by epsilon 2 is just a field, so it follows that this is a heredity chain. So in particular, this algebra A is a quasi-hereditary algebra. So this heredity chain is not unique for this algebra A. We can consider a different heredity chain. We can start from 0 and then embed it into the ideal generated by the trivial path in the first vertex. That ideal will also contain the element A. And again, it is easy to check that this is a heredity ideal in A, so we can embed this into A and get another heredity chain for A. So the heredity chain for a quasi-hereditary algebra is usually not unique. Let us do a highest weight example again. So assume that the category A mod is a highest weight category with respect to some choice of a linear order on the set of isomorphism classes of simple A modules. Let EI be a primitive idempotent which corresponds to the simple module Li, and assumes that we choose EI such that EI is equal to EI and is equal to 0 for all I not equal to j. So basically we fix a full set of pairwise orthogonal primitive idempotents for A. Then the projective module Pi is equal to A times EI, and let us denote by EI tilde the sum of EI plus 1, EI plus 2, and then all the way up to EM. Theorem. The algebra A is quasi-hereditary with a heredity chain given as follows. So we start from 0, then we embed it into the two-sided ideal generated by EM tilde. This we embed into the two-sided ideal generated by EM minus 1 tilde, and then all the way up to the two-sided ideal generated by E1 tilde, which is equal to A. Proof. Recall that we have established the inductive nature of highest weight categories. If we have a highest weight category, and we consider the Serre subcategory generated by all simples except the last one, the maximal one, then we again get a highest weight category. Previously, we have proved that the ideal generated by the idempotent, which corresponds to the maximal simple in our partial order, is a heredity ideal. If we factor this heredity ideal out, we get exactly the algebra, which is behind the Serre subcategory generated by the remaining simple modules. And so we can use the inductive nature of highest weight categories to show that I2 modulo I1 is a heredity ideal in A modulo I1, and then proceed by induction. In this way, we show that if we have an algebra whose module category is a highest weight category, then this algebra has this heredity chain and hence is a quasi-hereditary algebra. Now we want to reverse this. We want to prove that if we have a quasi-hereditary algebra, then its module category is a highest weight category. For this, we need to define a linear order based on the datum which defines a quasi-hereditary algebra. First of all, let us note that any ideal of a semi-simple finite-dimensional algebra is generated by an idempotent. Therefore, since the Jacobson radical is nilpotent and the quotient by it is semi-simple, any ideal I of A, which is idempotent, is also generated by some idempotent element in A. Now assume that A is quasi-hereditary with a fixed heredity chain as in the definition of a quasi-hereditary algebra. From this datum, we want to define some linear order on the set of isomorphism classes of simple A modules. So let E be the idempotent that generates the ideal I1. We consider the projective module AE, pick some linear order on the simples which appear in the top of this module, and we declare this to be the maximal segment for our linear order less than or equal to. So here we make some choice, we pick some linear order on the simples which appear in the top of the projective, which corresponds to the idempotent defining the ideal I1. Now we proceed by induction. So let E prime be the idempotent that generates the quotient of I2 modulo I1. So we look at the algebra A modulo I1 and at the corresponding projective module A modulo I1 times E prime. We pick some linear order on the simples that appear in the top of this module and declare this to be the segment in our partial order, which is just below the previous segment. And now we proceed inductively and define the rest of our partial order. So for example, we have seen that the path algebra A of the quiver, which has two vertices 1 and 2, and an arrow A from 1 to 2, so this algebra is quasi-hereditary for the heredity chain, which starts with 0, and then goes to the ideal generated by epsilon 2, and then goes to A. So the starting ideal is the one which is generated by epsilon 2, which means that the simple module L2, which corresponds to epsilon 2, this will be the highest element with respect to this order, and the simple module L1 will be smaller than L2. We also have seen that this is not a unique heredity chain for our algebra. We can also consider the heredity chain, which starts with the ideal generated by epsilon 1, and then this embeds into A. So since the ideal here is generated by epsilon 1, we will get that our simple module L1 is maximal with respect to our linear order, and L2 is the next one. So now we can formulate the inverse relation between quasi-hereditary algebras and highest weight categories. Theorem: if A is a quasi-hereditary algebra and our order is as defined above, so this is the order which we just constructed on the set of isomorphism classes of simple A modules, then the category of A modules with respect to this order is a highest weight category. Proof. Let us look at the ideal I1, which is equal to A, EA. So here E is the idempotent, which generates the idempotent ideal I1. From the condition that I1 times the Jacobson radical times I1 is equal to 0, we of course get that E times Jacobson radical times E is equal to 0. In other words, if we consider the radical of the projective module AE, then no simple appearing in the top of AE appears in this radical as a subquotient. So now let Lm be maximal as defined above. So we have chosen some linear order on the set of simples which appear in the top of AE, and let Lm be the maximal one. Then we have just proved that if we consider the radical of Pm, then Lm doesn't appear there. So the multiplicity of Ln in Pm is 1. Also, the trace of AE in A is of course AEA, which is I1 by definition, and so this is a projective module because we have a heredity ideal. Hence, the trace of Pm in our algebra A is projective, and thus it is some sum of copies of Pm. And similarly, we can actually argue for all other summons which appear in AE. Now we can factor out the heredity ideal I1 and proceed by induction. And in this way, we will prove that all projective modules have a standard filtration. And then if we look at the definition, we see that the first condition in the definition of quasi-hereditary category is satisfied due to the construction of standard modules, and then this proof for Lm, which we then repeat inductively, that the multiplicity of Lm in Pm is 1, and then the condition that projective modules have standard filtrations. It follows from this observation that the trace of Pm in A is a direct sum of copies of Pm, and then again it's completed by induction. So this completes the proof of this theorem. So let us sum up what we have just proved. We have just proved that the category of modules over a quasi-hereditary algebra is a highest weight category. We also proved that if the category of modules over some algebra is a highest weight category, then this algebra is quasi-hereditary, and that the order in the definition of the highest weight category determines a heredity chain and vice versa. In other words, the notions of a quasi-hereditary algebra and the highest weight category, they are in a certain sense equivalent. It's just the point is that quasi-hereditary algebra emphasizes the algebra itself, while a highest weight category emphasizes the category of modules over this algebra. So in this course, we will study quasi-hereditary algebras and their highest weight categories of modules. Now let us define the category F delta, the category of modules with a standard filtration. So let A be a quasi-hereditary algebra, and L1, L2, and so on Ln be our list of simple modules written with respect to the highest weight order. So let delta 1, delta 2, and so on delta m be the corresponding standard modules. Definition: a standard filtration of a module M is an A module. A standard filtration of M is a filtration whose subquotients are standard modules. In other words, we have a filtration of M which starts from 0, this is M0, goes to M1, M2, and so on, all the way up to MR, which is M. And the condition is that for any I from 1 to R, the quotient of Mi modulo Mi minus 1 should be isomorphic to some standard module, so delta Ji, where Ji is some index from 1 to M. We denote by F delta the full subcategory of A mod, consisting of all modules that admit a standard filtration. Let us note that by the conditions imposed on highest weight categories and quasi-hereditary algebras, if you have a quasi-hereditary algebra, then all projective modules over this algebra belong to F delta. Similarly, we can define the category F nabla of all modules with a costandard filtration. Again, let A be a quasi-hereditary algebra. L1, L2, and so on Lm be a full list of simple A modules written with respect to the highest weight order. Nabla 1, nabla 2, nabla m be the corresponding list of costandard modules. Then we define a costandard filtration of some A module M as a filtration whose subquotients are costandard modules. So we have a filtration of M, which starts with 0, this is M0, this embeds into M1, this in M2, and so on, all the way up to MR, which is M, such that for any I between 1 and R, the quotient of Mi modulo Mi minus 1 is isomorphic to some costandard module nabla Ji. So here Ji is some index from 1 to M. Notation: we denote by F of nabla the full subcategory of A mod, which consists of all modules that admit a costandard filtration. And we note that all injective modules over a quasi-hereditary algebra do have costandard filtration, so they belong to F nabla. Now let us establish some basic homological comparisons between these categories F delta and F nabla. So let A be a quasi-hereditary algebra. Recall that last time we have established that the families of standard and costandard modules are homologically orthogonal to each other. This means that the dimension of the space of all case extensions over A from delta I to nabla J, so this dimension is equal to 1 if I is equal to J and K is equal to 0, and this dimension is equal to 0 otherwise. Corollary: for any module A with standard filtration and any module Y with a costandard filtration, we have that x over A of degree k from x to y is equal to 0 for all k greater than 0. Proof: to prove the statement, we proceed by induction with respect to the lengths of a standard filtration in X and a costandard filtration of Y. The basis of the induction is the case where X is a standard module and Y is a costandard module, and then this reduces to the fact which we established last time. Let us do the induction step for X, and for Y the induction step is similar. To assume that X is not a standard module, then we have a standard filtration of X. It starts from some delta I, which embeds into X, and we have a cokernel X prime, which is in F delta. So we take this short exact sequence and apply the functor of taking home into Y over A. So this yields an exact sequence. We have the long exact sequence, which is given by applying this functor, and in that long exact sequence, we have a short segment for extensions of degree k, which looks as follows. So we have x over a of degree k from x prime to y goes to x over a of degree k from x to y, and this goes to x over a of degree k from delta I to y. So now here, the lengths of the standard filtration of x prime and delta I are smaller than that for x. So the left-hand side and the right-hand side are 0 by the inductive assumption, and so the middle term is also 0. So this establishes the induction step in case the standard filtration of x has lengths greater than 1. And then one also has a similar induction step in the case when the co-standardly filtered module y has a co-standard filtration of lengths greater than 1. Putting this together, the proof is completed by induction. So now we have defined the categories of modules with a standard and a co-standard filtration. A natural question here, if we have a module with standard filtration, the standard filtration doesn't have to be unique. Do we have some version of Jordan-Hölder's theorem for standard filtration? Can we say that the multiplicities of standards appearing in a standard filtration are well defined? So let's discuss this. So let A be a quasi-hereditary algebra proposition for any module X with standard filtration over A, and any index I between 1 and m, the multiplicity of delta I as a subquotient of a standard filtration of X is independent of the choice of this filtration, and it equals the dimension of the space of homomorphisms over A from X to nabla I. Proof. Proof is actually the same as the proof of the statement in the previous slide, but on the previous slide we concentrated on x's, and now we concentrate on hops. So we proceed by induction on the lengths of the standard filtration of X. The basis of the induction is the case where X is a standard module, and there we just use the formula from the last lecture. Then the dimension of the Hom space over A from delta J to nabla I is equal to the canonical symbol delta ij. So it is 1 if I is equal to j, and it is 0 otherwise. Now for the induction step, we assume that X has a standard filtration of lengths greater than 1, take a standard submodule delta j of X, and assume that the cokernel X prime has a delta filtration. We apply Hom over A blank nabla I, and this yields the following starting part of the long exact sequence. So we start from 0, then we have Hom from X prime to nabla I, then we go to Hom from X to nabla I, then to Hom from delta J to nabla I, and then to X1 from X prime to nabla I. But X prime has a delta filtration, and nabla is a nabla, so this X1 vanishes. So this X1 is equal to 0, and so we get a short exact sequence. In other words, Hom from X to nabla I has as a submodule Hom from X prime to nabla I, and as a quotient Hom from delta J to nabla I. And we see that this Hom behaves additively with respect to short exact sequences with delta filtered subquotients, similarly as the multiplicity. It also behaves additively. And now the claim of the proposition follows from the inductive assumption. Similarly, we can prove the well-definedness for the multiplicities in F nabla. If A is a quasi-hereditary algebra, then for any module Y with co-standard filtration, and for any I between 1 and m, the multiplicity of nabla I as a subquotient of a co-standard filtration of Y is independent of the choice of such a filtration and is equal to the dimension of the Hom over A from delta I to Y. And this is proved similarly to the case of modules with standard filtration. We remark that one can give an alternative argument for both propositions. Since the algebra A is quasi-hereditary, then its module category is a highest weight category, then the classes of standard or co-standard modules form a basis in the Grothendieck group of A mod. Now, given a module X with standard filtration, the multiplicity of delta I in X must coincide with the coefficient of the class of X in the Grothendieck group when written in the basis consisting of the classes of standard modules. Similarly, if we have a module Y with nabla filtration, then the multiplicity of nabla I in Y must coincide with the coefficient when we write the class of Y with respect to the basis given by the classes of co-standard modules. So that's an alternative proof for the fact that the multiplicities of standard, respectively co-standard modules in the corresponding filtrations are always well defined. Now we can finally formulate and prove one of the most famous results about quasi-hereditary algebras, which is called the Brouwer-Humphreys BGG reciprocity. Here BGG means Bernstein, Gelfand, Gelfand, so the Israel Gelfand and Sergei Gelfand. Recall that if algebra A is quasi-hereditary, then all projectives have standard filtrations and all injectives have co-standard filtrations. Theorem: let A be a quasi-hereditary algebra. Then, for all indices I and j between 1 and m, the multiplicity of the standard module delta j in a standard filtration of Pi equals the multiplicity of the simple module Li in a composition series of nabla j. And similarly, the multiplicity of the costandard module nabla j in a costandard filtration of II is equal to the composition multiplicity of Li in delta j. Proof? Of course, we prove the first claim and the second is similar. So by the previous proposition, the multiplicity of delta j in Pi equals the dimension of the home space from Pi to nabla j. But that's more or less the definition of the composition multiplicity of Li in nabla j. And we are done. And the second statement is similar. We can also consider the special case, and this is a situation when our algebra A has a simple preserving duality star. In this case, all simple modules are self-dual, projectives are dual to the corresponding injectives, and standard modules are dual to the corresponding costandard. In particular, the multiplicity of Lj in delta I equals the multiplicity of Lj in nabla I for all I and j. We can now formulate it as a corollary, assume that A is quasi-hereditary and has a simple preserving duality. Then, for all I and j, the multiplicity of delta j in Pi equals the multiplicity of Li in delta j. And similarly, the multiplicity of nabla j in II equals the multiplicity of Li in nabla j. Note that, in this case, we also have the following: that the multiplicity of Lj in Pi, that is, of course, the dimension of the homomorphism space from Pi to Ij, applying the duality, we can rewrite it as a dimension of the home space from Pj to Ii, which is, of course, the multiplicity of Li in Pj. So in other words, the Cartan matrix of our algebra A is symmetric. So if A has a simple preserving duality, then the Cartan matrix of A is symmetric. We can see the same thing using the BGG reciprocity. Indeed, the multiplicity of Lj in Pi can be written as a sum over all S, and we take the multiplicity of delta S in Pi and we multiply with multiplicity of Lj in delta S. Now, by the BGG reciprocity, the multiplicity of delta S in Pi is the same as the multiplicity of Li in delta S. And the multiplicity of Lj in delta S is the same as the multiplicity of Pj in delta S. And then when we combine this, we get the multiplicity of Li in Pj. Here is an example. Consider the path algebra A of the following quiver with relations. So we have two vertices, 1 and 2, the arrow alpha from 1 to 2, and the error of beta from 2 to 1. And the relation is that alpha beta is 0. And on the previous lecture, we saw that this algebra has a simple preserving duality induced by the automorphism of this algebra, which swaps alpha and beta. We have also computed the diagrams of projective and standard modules. So P1 has top 1, then the middle part 2, and the socle 1. P2 has top 2 and socle 1. Delta 1 is just the simple module L1, and delta 2 is P2, so it has top 2 and socle 1. And so this algebra is quasi-hereditary, and we immediately see that the multiplicity of delta 1 in P1 equals the multiplicity of L1 in delta 1 and is equal to 1. The multiplicity of delta 2 in P1, so here we have one copy of delta 2 in P1, equals the multiplicity of L1 in delta 2 and is equal to 1. There is no delta 1 in P2, and there is no L2 in delta 1, so these multiplicities are 0. And finally, there is one delta 2 in P2, and there is one L2 in delta 2. So these two multiplicities are 1. Okay, some extra problems and questions at the end. Problem question 1. Show with all details that, for an ideal I of A, the condition that II is equal to I is equivalent to existence of an idempotent E in A, such that I is generated by E. Problem question 2. Write with all details the induction with respect to Y in the corollary about the extension vanishing between F delta and F null. Problem question 3. Prove the proposition about filtration multiplicities in costandard filtrations with all details. Problem question 4. Explain why, for a quasi-hereditary algebra A, the classes of standard or costandard modules form a basis in the Grothendieck group of A mod. And problem question 5. Prove with all details that the multiplicity of nabla J in II is equal to the multiplicity of Li in delta J for a quasi-hereditary algebra A. Thank you very much and see you next time.